In this lecture, I am going to present what are the step-by-step procedure for the analysis of continuous beam by stiffness matrix method. Then I would like to solve one problem based on the two-span continuous beam with one end is fixed and other end is simply supported. Then coming to the steps which are used for the analysis of continuous beam by stiffness matrix method. These are the different steps. In this method, first determine the degree of kinematic indeterminacy, that is degree of freedom. Then identify the independent displacement components. Then assign the coordinate directions to the independent displacement components. Then prevent all the independent displacement components to obtain the restrained structure. Then determine the forces developed in each of the coordinate directions of a fully restrained structure due to external loading other than those acting at the coordinates. Then determine the stiffness matrix K by giving unit displacement to the restrained structure in each of the coordinate direction and find the forces developed in all the coordinates. Then compute the final forces in the coordinate direction, that is denoted by P. So here from the stiffness equation, P is equal to P dash plus P delta, P is equal to P dash plus K into delta, where K is the stiffness matrix and delta is the displacement matrix and P dash is the force matrix. Then use the condition of equilibrium of forces to compute the displacements in the coordinate directions. The displacement is equal to inverse of the stiffness matrix into P minus P dash. Then after knowing the displacements, compute the internal member forces by using slope deflection method. Then coming to one problem, analyze the continuous beams shown in figure by stiffness matrix method. So this is the two-span continuous beam. A, B, C. Support A is fixed and support C is simply supported. And span AB length 4 meter and span BC length 3 meter. On the span AB, uniform distributed load of intensity 60 kN by meter present throughout the length. And on the span BC, 100 kN load is present at the midpoint of the BC. So first find out the degree of kinematic indeterminacy. The degree of kinematic indeterminacy dk is equal to 3j minus r plus m, where j is the number of joints, r is the number of external reaction components and m is the number of members. But here the number of joints, 3 joints, A, B, C, 3 joints, the number of joint is equal to 3 and number of reaction components is equal to 3 plus 1 plus 1, 5, and number of members is equal to 2, AB and BC. So J is equal to 3, R is equal to 5 and M is equal to 2. Then dk is equal to 3j minus r plus m, 3 into 3 minus 5 plus 2, this is equal to 2. So the degree of kinematic indeterminacy or the degree of freedom is equal to 2. Because at support A, due to fixed end, there is no displacement takes place. At support B, due to the roller support, there is no vertical displacement takes place. And at support C also, there is no vertical displacement takes place. Only the rotational displacement takes place at B and rotational displacement takes place at C. So in this problem, there are 2 degrees of freedom. The unknown displacements in this problem are the rotation at B and rotation at C. Hence, the coordinates selected at B and C are shown in figure. So, as the degree of freedom is 2, so the rotation takes place at B and C. So, the coordinate selected at B and C. The coordinate 1 is selected at B and coordinate 2 is selected at C. This is the continuous beam with assigned coordinates. So, in this case, this is the fully restrained structure. So, here first find out the forces in the restrained structure in the coordinate direction due to the external loading. So, here prevent all the independent displacement components and obtain the restrained structure. So, here apply the fixed end to all the supports, that is to the support A and to the support B and to the support C. So, make all the supports are restrained or fixed and find out what is the forces at the coordinates 1 and 2. First find out what is the fixed end moments at the end of the beam, then find out what is the forces due to the external loading. So, here first find out the moment MFAB, MFBA. MFAB is equal to minus 60 into 4 square by 12 and MFBA is equal to plus 60 into 4 square by 12 and MFBC is equal to minus W 100 into 3 by 8 and MFCB is equal to plus 100 into 3 by 8. This is the fixed end moments MFAB minus 60 into 4 square by 12. This is minus 80 kilonewton meter. MFBA plus 60 into 4 square by 12. This is plus 80 kilonewton meter. MFBC minus 100 into 3 by 8 is equal to minus 37.5 kilonewton meter. MFCB is equal to plus 100 into 3 by 8 is equal to plus 37.5 kilonewton meter. So, these are the fixed end moments at the end of the members. Then find out the forces in the coordinate direction 1 and 2. So, the P1 dash is equal to MFBA plus MFBC and P2 dash is equal to MFCB. P1 dash is equal to MFBA plus MFBC. So, this is equal to 80 minus 37.5 is equal to plus 42.5 kilonewton meter. Then P2 dash is equal to MFCB is equal to plus 37.5 kilonewton meter. These are the forces in the restrained structure in the coordinate direction due to the external loading. The above forces are positive if they act in the positive direction of the coordinate. Then find out the stiffness matrix. Here determine the stiffness matrix by giving unit displacement in the restrained structure in each of the coordinate direction and find the forces developed in all the coordinate directions. And it is assembled using the slope deflection equations. So, apply unit displacement in coordinate direction 1 first, end A is fixed, end C is fixed, and apply unit displacement in coordinate direction 1. This is the restrained beam with unit displacement in coordinate direction 1, theta B is equal to 1. Then due to this unit displacement, find out what is the force developed in coordinate 1 and find out what is the force developed in coordinate 2. So, K11 is the force developed in coordinate direction 1 due to unit displacement at 1. K21 is equal to force developed in coordinate direction 2 due to unit displacement at coordinate 1. 1 radian rotation is given to support B in coordinate direction 1. Then the forces developed in the coordinate direction 1 and 2 are found by using the slope deflection equation. Then find out the K11 from the span AB and from the span BC. So, from span AB, so here 4EI theta B by L plus 2EI theta A by L, and from the span BC 4EI theta B by L plus 2EI theta C by L. But the span length AB is given 4 meter and span length BC is given 3 meter. and the end conditions theta A is equal to 0, theta C is equal to 0 and theta B is equal to 1. So put the end conditions in this expression, then K11 is equal to 4 EI theta B by 4 plus 4 EI theta B by 3 is equal to 7 EI theta B by 3. But theta B is equal to 1. So after substituting the theta B value here, so K11 is equal to 7 EI by 3. Then find out K21. So here K21 is equal to 4 EI theta C by L plus 2 EI theta B by L. 4 EI theta C by 3 plus 2 EI theta B by 3. Then after putting the value of theta B and theta C in this expression, so K21 is equal to 2 EI theta B by 3, then K21 is equal to 2 EI by 3. So this is the forces at coordinate 1 and coordinate 2 due to unit displacement at coordinate 1. Then apply unit displacement in coordinate direction 2. Make all the supports are restrained. A is restrained, B is restrained, and apply the unit displacement at coordinate C. Theta C is equal to 1. And due to the unit displacement at coordinate C, find out what is the forces developed at coordinate 1 and what is the force developed at coordinate 2. That is the force developed at coordinate 1 due to the unit displacement at coordinate 2, that is equal to K12. Similarly, the force developed at coordinate 2 due to unit displacement at coordinate 2, this is equal to K22. So find out K12 and K22. So this is the restrained beam with unit displacement in coordinate direction 2. 1 radiant rotation is given to support C in coordinate direction 2. Then the forces developed in the coordinate direction 1 and 2 are found by using the slope deflection equations. So here find out what is the force developed at coordinate 1 due to unit displacement at coordinate 2. So here K12 is equal to 4 EI theta B by L plus 2 EI theta C by L. 4 EI theta B by 3 plus 2 EI theta C by 3. Then the end conditions here, theta A is equal to 0, theta B is equal to 0 and theta C is equal to 1. So put the end conditions in this expression, then K12 is equal to 2 EI by 3. Similarly, find out the K22. K22, the force developed at coordinate 2 due to unit displacement at coordinate 2. K22 is equal to 4 EI theta C by L plus 2 EI theta B by L. 4 EI theta C by 3 plus 2 EI theta B by 3. Then K22 is equal to 4 EI by 3. Then the final forces which is acting in the coordinate direction 1 and 2 are 0. There are no forces at coordinate 1 and 2. So P is equal to P1, P2, that is equal to 0, 0. Then the stiffness equation, P is equal to P dash plus K into delta. K is the stiffness matrix and delta is the displacement matrix and P is the force matrix. Then K delta is equal to P minus P dash. But here we got the stiffness matrix K11, K12 and K21 and K22. So K11 is equal to 7 EI by 3 and K12 is equal to 2 EI by 3 and K21 is equal to 2 EI by 3 and K22 is equal to 4 EI by 3. And this is the displacement at coordinate 1 and coordinate 2. Then this is the final forces P1, P2 at coordinate. There are no forces at coordinate 1 and 2. So P1 is 0, P2 is 0. And this is the force due to the external loading P dash, P1 dash and P2 dash. Then simplify this expression. Then after taking the common EI by 3, 7224 delta 1 delta 2 is equal to minus 42.5 minus 37.5. So here delta 1 delta 2 is equal to 3 by EI, 7224 minus 1 minus 42.5 minus 37.5. So this is the inverse of the stiffness matrix. Then determine the inverse of the stiffness matrix. So delta 1 delta 2 is equal to 3 by EI, 1 by 7 into 4 minus 2 into 2, then 4 minus 2 minus 2 7 into minus 42.5 minus 37.5. Then multiply the inverse of the stiffness matrix with the force matrix. Delta 1 is equal to minus 11.875 by EI and delta 2 is equal to minus 22.188 by EI. So delta 1 is equal to theta b is equal to minus 11.875 by EI and delta 2 is equal to theta c is equal to minus 22.188 by EI. But theta a is equal to 0 due to fixed end. So here you got theta a is 0 and the displacement you got at coordinate 1 theta b and the displacement at 2 got theta c. That is delta 1 is equal to theta b and delta 2 is equal to theta c. So this is the displacement at coordinate 1 and coordinate 2. Then find out the final moment by using the slope reflection equations. So here MAB is equal to MFAB plus 4EI theta A by 4 plus 2EI theta B by 4. So here you got theta A, theta B and theta C. So theta A is equal to 0 and theta B is equal to minus 11.875 by EI and theta C is equal to minus 22.188 by EI. So put the value of theta A and theta B here. Then MAB is equal to minus 85.938 kilonewton meter. Then find out MBA. MBA is equal to MFBA plus 4EI theta B by 4 plus 2EI theta A by 4. Then put the value of theta B and theta A in this expression. So here MBA is equal to 68.125 kilonewton meter. Then find out MBC. MBC is equal to MFBC plus 4EI theta B by 3 plus 2EI theta C by 3. So here put the value of theta B and theta C here and also put the value of fixed end moments MFBC. So MBC is equal to minus 37.5 4EI by 3 into minus 11.875 by EI plus 2EI by 3 into minus 22.188 by EI. Then MBC is equal to minus 68.125 kilonewton meter. Then find out MCB. MCB is equal to MFCB plus 4EI theta C by 3 plus 2EI theta B by 3. So MFCB is equal to 37.5 and theta C is equal to minus 22.188 by EI. Theta B is equal to minus 11.87 by EI. So put the value of theta B, theta C and MFCB here and find out the MCB. This is equal to 0. As you know, if the end is simply supported, so the moment at the end is equal to 0. MCB is equal to 0. Here also you got the value 0. So these are the summary of final moments. MAB is equal to minus 85.938 kilonewton meter. MBA is equal to 68.125 kilonewton meter. MBC is equal to minus 68.125 kilonewton meter and MCB is equal to 0. Then give the direction of the moments. So here MAB minus 85.938 kilonewton meter negative. So the direction of the moment is anti-clockwise. Anti-clockwise direction 85.938 kilonewton meter. Then MBA is equal to 68.125 kilonewton meter. So here the value is positive. So apply the direction clockwise. Then MBC is equal to minus 68.125 kilonewton meter. And due to the negative value, apply the direction anti-clockwise. And MCB is equal to 0. But at the joint B, the sum of the moments should be 0. So here you got MBA plus MBC is equal to 0. 68.125 minus 68.125. So this is equal to 0. This is the direction of the moments. Then draw the bending moment diagram. So here you know this is the support moment. MAB is equal to 85.938 kilonewton meter. So here you draw 85.938 kilonewton meter. And here 68.125 kilonewton meter. So here 68.125 kilonewton meter and here 0. Then draw this points. So this is the negative bending moment diagram. Then you know what is the load is given on the beam. On the span AB, that is having 60 kilonewton by meter UDL throughout the span. So find out what is the maximum positive moment on the span AB. So this is equal to W L square by 8. So W is given 60 kilonewton by meter and L is given 4 meter. So 60 into 4 square by 8 is equal to 120 kilonewton meter. Similarly, the maximum positive moment on span BC here. So the load is present at the midpoint of the BC. Here the maximum positive moment, this is equal to W L by 4. 100 into 3 by 4. 100 into 3 by 4, this is equal to 75 kilonewton meter. So this is the maximum positive moment on span BC and maximum positive moment on span AB. As the load is UDL on the span AB, so the bending moment diagram is parabolic and the total this ordinate is 120 kilonewton meter. Similarly, on the span BC, so the load is present at the midpoint. Here this is the triangular shape, the positive bending moment diagram. The positive bending moment diagram or free bending moment diagram is triangular shape, and this ordinate is 75 kilonewton meter. Then you can find out what is the maximum positive moment here and what is the maximum positive moment here. Then you can find out what is the positive moment on the span AB and maximum positive moment on the span BC. If you know this ordinate, then you can find out what is the maximum positive moment on the span AB and on the span BC. So on the span AB, so here you know this ordinate is 85.938 kilonewton meter and here this is 68.125 kilonewton meter. So here you will get the maximum positive moment at the midpoint. Take the average of these two ordinate. So this ordinate is equal to 77.03 kilonewton meter. Then the total is 120 kilonewton meter. So from this total you deduct this one, then you get what is the positive moment on the span AB. So this is 120 minus 77.03 is equal to 42.97 kilonewton meter. Similarly here find out this ordinate, because you know this is 68.125 and this one is find out by 2 because this is the 3 meter, and 68.125 by 3 is equal to x by 1.5. X is equal to 68.125 by 2. So this is equal to 34.06 kilonewton meter, this ordinate. But the total ordinate you know 75 kilonewton meter. Then you find out what is the maximum positive moment on the span BC. So 75 minus 34.06 kilonewton meter, that is equal to 40.94 kilonewton meter. This is the maximum positive moment of the span BC. So this is the final bending moment diagram. Negative, this is positive, negative, positive. And here this portion is cancelled due to the positive and negative, and this portion is also cancelled due to positive, negative. So this is the final bending moment diagram of this continuous beam. Now all are clear how to find out the moments using the stiffness matrix method, then how to draw the bending moment diagram.